Hello, everyone. Today we are going to talk about Taylor polynomials and applications of Taylor polynomials. First, let's start with definition. Let's imagine that we have function f of x represented as a sum of infinite series, which are Taylor series. So function is good differentiated n times or infinitely many times differentiated. And general term is going to look like this, right? And from 0 to infinity. Let's consider partial sum of this series, partial sum. And label it as Tn. And this partial sum is not going to have infinitely many terms, but it's going to have finite amount of terms. I'm going to write it down like this. Fi at a x minus a to the power of I over I factorial. And here I from 0 to n. Let's consider first n plus 1 terms of this series. So term number 0 until term n plus 1 terms. And here I placed I as a coefficient everywhere because I wanted to use n as a ending index of this power series. The partial sum is called Taylor polynomial. And when n goes to infinity, of course, Taylor polynomial will go to a function. So if you have all infinitely many terms, it's going to turn into this function infinite, which is represented as Taylor series. But if you consider it as a partial sum, it's going to approximate the function, right? So you can always say that Tn is approximately equal to a function, approximates a function. And I'm going to consider several polynomials. Let's consider e to the power of x and what kind of polynomials we are going to have. Let's write down e to the power of x is what? 1 plus x squared over 2 factorial, x cubed over 3 factorial, and so on. Well, what we have over here is Taylor polynomial at a equals 0, centered at 0, can be. And let's write down first few Taylor polynomials. T0 of x, partial sum of only one term is equal to 1. T1 of x is going to be 1 plus x. T2 of x is going to be 1 plus x squared over 2 factorial. Well, again, we label it as T2 because we kind of, first polynomial starts with 0. I'm going to do one more, T3. 2 factorial and x cubed over 3 factorial. So Taylor polynomials are not going to have lots of dots and lots of terms. They're going to have actually well, in general, they're supposed to have for example, if your number is n here, they're supposed to have n plus 1 terms. Sometimes some terms are going to be missing, but in general, that's what it's going to be. How they are going to be represented on the graph. I'm going to graph actually Taylor polynomials. Let's imagine this is 1, and this is probably another one. So I'm going to start at C. Let's do actually same scale on both x and y. 1 here, 1 here. So my 0 polynomial is going to look like this. X equals 1. Y equals 1. Sorry, that's my 0 polynomial. It's T0, right? 1 plus x. 1 plus x is going to look like this. T1 equals 1 plus x. And this is just 1. So I'm going to turn the color to red. My next one is 1 plus x squared. which is going to look like a quadratic polynomial and kind of going to look like this. Like next one, t cube is going to look like maybe like this, something like that. And if you graph actual function, actual e to the power of x, it's going to look like this. And it's going to become closer and closer to the like higher degree polynomial. So of course, zero polynomial approximates only around here, right? And the first degree polynomial approximates already bigger interval. And the higher degree polynomial is going to approximate the function better. My picture is not ideal. You can always look at the picture in the book. And I think in class, I'm going to give you more like pictures of different Taylor polynomials and how well they approximate function, how far. But for now, we are interested like in like how big is supposed to be polynomial to approximate function. Why do we use polynomials? It's kind of clear. Polynomials are much easier to integrate, to differentiate, just to do any stuff with them in comparison to just actually function e to the power of x, which is just describing for us a table of numbers, right? Um, well, we do have a remainder. Remainder is all terms we drop when we consider like n terms of the polynomial. Let's kind of write down by definition what is remainder. Remainder is like if you consider nth polynomial, everything beyond this is going to be called remainder. Well, let's see. If I consider T2, this one, as my polynomial, this is my T2, the rest of all the terms are going to be remainder of 2, R2. So it's not remainder of 2 terms. Actually, there are 3 terms and the rest is dropped, but just like how we label them, right? For remainder, guys, we are going to have a special formula to estimate how big is remainder. We're not going to prove it, but formula is not very complicated. It looks very much like the next term into Taylor series. Look at this. What we have, n plus 1 factorial, that's the next term, right? X minus a to the n plus 1, absolute value, almost next term. Normally it has like positive value, but we want to know just numerical value. The only thing here different is m. M here is going to be the maximum or any number greater than f n plus 1 derivative of x on interval on which we consider that polynomial on interval. Okay, so basically that's exactly nth term, just with little kind of details like here is absolute value of n plus 1 derivative on the interval, here is x minus a to the power of n plus 1 absolute value. Factorial is just like a factorial. Let's try to see how this is going to work. We understand that remainder will go to 0 if we increase n to infinity. If we increase n over here to infinity, of course, there's going to be almost no terms left, or the remainder is going to become just very small. Of course, there are going to be infinitely many terms left. Well, let's try to find a Taylor polynomial for a function. Like consider example. Approximate f of x equals cubic root of x at a equals 8 by Taylor polynomial of degree 2. So degree 2 means that my index here and my index here are going to be 2. Okay, how we do that? Well, first, guys, I'm going to write down like general expression, okay? And then we are going to do calculations. So my cubic root of x. Basically, guys, we don't know how to extract cubic roots unless we do use calculator, right? is going to be what? According to the formula, that's going to be f of a plus f of a prime x minus a over 1 factorial plus f of a 2 second derivative x minus a squared 2. And we don't need more terms because this is degree 2. So the highest degree of x is supposed to be 2. So we have just these 3 terms. Pay attention to like what usually polynomials are counted by degrees or named by degrees. So what we need to kind of represent it as Taylor polynomial, we need to know what is f of a. In our case, it's f of 8. And in our case, it's a cubic root of 8, which is going to be 2. Very nice. Now we need a derivative. Derivative f of x is going to be what? Well, this is x to the power of 1 over 3, which means that we are going to have 1 over 3 x to the power of negative 2 over 3. I'm going to write it down like this. 1 over 3 here, cubic root of x squared. It's a little bit crazy, but just if you want to substitute everything, it's going to be a little bit easier. Cubic root of 8 squared. Well, we can extract cubic root of 8. It's 2 squared, it's 4, and we are going to have 1 over 12. Very nice. We just have one more thing to calculate. X. I'll differentiate this one. It's 1 over 3 by negative 2 over 3. And x to the power of minus 1 is going to give me minus 5 over 3. Which is going to give me, let's say, 2. 3 and 3 is 9. I'm going to make it like a smaller fraction. I multiplied all the numbers here. And then we'll need to substitute 8 here, right? So it's cubic root of 8 to the power of 5. Which is going to give me minus 2 over 9. Cubic root of 8 is 2. So 2 to the power of 5 is 32. Or actually, if we cancel 1, 2 with this one, it's going to be 1 over 9 by 16. And I forgot minus. I'm getting minus 1, 4, 4. That's going to be my coefficient. Now I'm going to just plug all these coefficients, this one, and this one, into my formula. And that's going to produce for me Taylor polynomial. Why don't I just continue and write down 2. Derivative is 1 over 12. 1 factorial is nothing, right? And here x minus 8, my a is equal 8. And minus 1 or 4, right? And this is just a derivative. Now, we also need a factorial. I'm going to write on 2 factorial. And also x minus 8 squared. So that's a polynomial. That's a T2 of x for cubic root nearby 0.8. Okay. Okay. Well, maybe we should multiply 144 by 2 and get 288. I'm going to do it. 288. And this one just disappeared, right? Very good. So we have a polynomial now. How good this polynomial approximates my function on interval? Let's consider interval. For example, from 6, no, from 7 to 9. Why from 7 to 9? Well, if we have 0.8 over here, right? 7 is here and 9 is here. 7 and 9. So kind of plus minus 1 actually from my 0.8. So I'm going to calculate my R2 estimation by my formula m over n plus 1 factorial x minus a to the power of n plus 1. So what I'll need first, m. m is greater or equal than n plus 1 derivative on interval, right? So I'll need to differentiate this one more time. And the derivative is going to be minus 2 over 9 by minus 5 over 3, x to the power of plus 3, that's 8 over 3 minus. So basically, I'm going to have, all of it, multiply everything, that's 10, and here 9 by 3, 27, right, 2 plus, and 1 over cubic root of x to the power of 8. Here, guys, we'll need to figure out what is a maximal value of this on interval from 7 to 9. Well, the fraction is bigger if we divide by a smaller number. So smallest number on this interval is 7. That's just going to be approximately 10 over 27, 1 over cubic root of 7 to the power of 8. I'm going to calculate this number because we'll need to know the number. Okay, guys, my calculations are telling me that this number is 0.02, well, approximately. So we can use it as number m because m can be equal to this number. Or we can make it a little bit bigger, 0.03, for example. So now we probably are going to plug this number over here and estimate the whole thing. I'm going to write down R2 less or equal. So m, well, let's do it 0.00, I don't know, 3. Just make it bigger. Okay, n plus 1 factorial. So n is 2, so it's a 3 factorial. And x minus 8, n plus 1 is going to be like actually cube, right? Well, when x belongs to the interval from 7 to 9, like 7, 9 over here, and this is 8. What is going to be the biggest difference over here? Well, when x is sitting over here or over here, the biggest difference is going to be 1 unit. So basically, this one is going to be the biggest value of this is 1. Right? And we are going to have approximately, let's do this, cancel 3, 0.00 over 2, 1 over 2, 0, 5. That's my approximation. Well, actually, that's a good approximation, right? So this polynomial we have over here, I'm sorry, I'm going to rewrite the polynomial, okay? T2, it's going to be 2 plus what we have, 1 over 12 x minus 8 minus 1 over 288 x minus 8 squared, I guess, right? Let me double check it. I'm trying to figure out if I'm missing anything. Yeah, so this polynomial, which is a complicated quadratic function, approximates my actual function, which is like a cubic root of x, right? With very good accuracy on interval from 7 to 9, nearby 8. It approximates with accuracy 0.05. So actually we can, if we don't need more accuracy, we can use quadratic function instead of actually cubic root of x, for which we don't know the value. For quadratic, we even can calculate manual with hands, not only with calculator, right? Okay, that's how we apply a Taylor polynomials. So mostly we can do estimates of functions like we did in a previous section. We're estimating sine and cosine using like Taylor polynomials, and we'll also use to just substitute instead of actual function Taylor polynomial, which is going to simplify our life a little bit. And if you guys recall, the first two terms of Taylor polynomial, this one is linearization of a function. Remember linearization? Somewhere in calculus 5a, I was teaching my class. All of x linearization is f of x 0 plus f prime of x 0 x minus x 0. That's linearization of a function at point x 0. built on the first derivative. If you compare it, that's a value, that's a derivative, and that's x minus x0. So first two terms linearization, and this is kind of improving this linearization to get closer to the value of a function or on a longer interval. I think that's all about Taylor polynomials. So I think I'll see you in next lecture, and we are done actually with series chapter 11. Congratulations, guys.